All right, open up your book to section 10-4. We're on page 514 in your book. The title of this section is Quadric Surfaces and Inscribed Figures. So our objective here is, given the equation of a conic section, sketch the surface generated by rotating it about one of its axes and find the volume or area of a figure that's inscribed either in the plane bounded by the graph or in the solid region bounded by the surface. So we'll deal with the first part of this here, just understanding what the quadric surfaces are and being able to sketch those. And we'll tackle the inscribed figures and finding the volume or area of those in the second half of section 10.4. All right, so let's start out by defining what exactly a quadric surface is. A quadric surface is a surface that's defined by quadratic equations, which, if you go back to our Cartesian equation of a conic, that ax squared plus bxy plus cy squared, that big long equation with a, b, c, d, e, and f in it, that is a quadratic equation. But it's a surface defined by quadratic equations in three variables, x, y, and z. So the key is that it's three-dimensional here. So the equation that we've been working with is just for 2 dimensions. We're now going to rotate around some axis to introduce a third dimension to this, and we'll end up with a quadric surface. Now the equations we're going to deal with will still be just in 2 dimensions. We're not going to worry about trying to come up with the equations of these in 3 dimensions. But just understand that that's what a quadric surface is defined as, a quadratic equation defined in terms of 3 variables. So if you just continued on with that equation that we've seen, adding the z in there, and the additional possibilities of what z could be, that would give you a quadric surface when you sketch that. All right, so let's start with the parabola. Here's just a basic sketch of a parabola. And again, we're going to rotate around some axis here to go from 2 dimensions, the parabola, to a third dimension, a quadric surface. So the parabola has just one axis of symmetry. That's the line that goes right through the vertex. It's perpendicular to the graph there as it goes through the vertex. And so there's our parabola. If we take that parabola and we rotate it around its axis of symmetry, we end up with what's called a paraboloid. So a paraboloid is a surface, a quadric surface, that's formed by rotating a parabola about the axis of symmetry. So we can kind of sketch what that looks like here. And I would suggest that you need a little bit, probably a practice of this on your own there. So sketching a few parabolas and then trying to sketch what this looks like when you rotate it around the axis would be helpful. But here's what we should end up with. Now, a parabola goes on forever here, so they would have to define some domain or range that you're working in. So we've defined that here. We've stopped this parabola at this point here. But the top of it is going to be something like this. That represents the top of it. And then we should draw a few more of these. These should kind of be parallel to the ones we've already marked. Use solid lines for the lines that should be in front and dashed lines for what's in behind. And we should end up with something that looks like this. We've got ourselves a nice little paraboloid. It's been rotated around its axis of symmetry. All right, let's talk about the ellipse. The ellipse actually has 2 axes of symmetry. One is called the major axis and one is called the minor axis. The major axis is the longer one. The minor axis is the shorter one. So in this case, my major axis is horizontal, but just realize it's not always horizontal. So whatever one is longer. And the minor axis is vertical in this case because of the way I've got my ellipse sketched here. We've got a major axis and a minor axis. So that means that I could actually rotate this around its major axis and get one sketch, or I could rotate it around its minor axis and get a different sketch. So what happens when we rotate this around its axis of symmetry? We get what's called an ellipsoid. Ellipsoid is kind of the general term that we use to describe this. The ellipsoid is a surface formed by rotating an ellipse about the major or the minor axis. And of course, since you have two axes of symmetry here, then that means you could actually end up with two possible sketches here. And actually, we give each one their own name here. And we kind of change the name a little bit. We go from ellipsoid to spheroid. I don't have a history on why the name of this, why this is called a prolate spheroid, but that's what the name is given to this. A prolate spheroid is the ellipse rotated around its major axis. When you rotate about the major axis, that surface you end up with is called a prolate spheroid. So in this case, we're rotating. I'm going to go ahead and mark that. We're rotating around our major axis, so that's this axis right here that we're talking about. So let's sketch what this would look like here after we rotated around that axis. So I'm going to sketch it kind of like this. So you kind of do the same thing that we did there with the paraboloid. Have a solid line for what's in front and a dashed line for what's behind. Let's draw a couple more of those. We'll draw one over here on the right side, and we'll do one over on the left side as well, just to try to give it some third-dimensional look to it. That right there is a pretty decent sketch of what a prolate spheroid looks like. And again, we're just ending up with the surface. It's not necessarily the solid of what's inside, but we're talking about the surface, the outside of this, the skin of it. Prolate spheroid. That's rotating around the major axis. So the last one here for the ellipse is rotating around the minor axis, and we call this the oblate spheroid. The oblate spheroid, rotation around the minor axis. This is the trickiest one of all to sketch. This one I would definitely suggest you give yourself a little bit of practice with, but we're rotating around the minor axis, so that's this axis right here that we'll rotate around. And maybe even look at the sketch they give you in the book. Now, the book, they do turn that a little bit to give you a perspective view of this in 3 dimensions. I'm not doing that here, but that might help you with understanding what this looks like here when you get done. But the prolate spheroid looks something like, or sorry, the oblate spheroid looks something about like this when we get done. Okay, it's coming out at us. It's almost like a pill shape here is what we should end up with. I'll draw a couple more of those in there. Maybe another one up here top. Okay. That's not too bad. That's an oblate spheroid. Like I say, that kind of has a pill shape to it maybe. The prolate spheroid up above, that looks almost maybe more egg shape or football shape. That's your 2 ellipsoids. All right, let's talk about the hyperbola. The hyperbola has 2 lines of symmetry as well. We call these the conjugate axis and the transverse axis. The transverse axis is the axis that goes through the vertices. Both of these go through the center. But the transverse axis also goes through the vertices of your hyperbola. And the conjugate axis doesn't touch the hyperbola at all. It's perpendicular to your transverse axis, and it goes through the center. So those are the 2 axes. So we have 2 lines of symmetry here then. So again, when we have 2 lines of symmetry, just like we saw with the ellipse, that means when we sketch this, there's 2 possible sketches we could have. So when we rotate around the transverse or the conjugate axis, we end up with a surface, a quadric surface. That's the surface formed by rotating the hyperbola about its transverse or conjugate axis. That's called the hyperboloid. Hyperboloid. And again, because there's 2 of these, we're going to give each one of them its own name. So let's start with rotating this around its transverse axis. This is what we call a hyperboloid of two sheets. And we'll see that there's kind of two parts of this, is why we call it the hyperboloid of two sheets. In fact, this almost looks like the paraboloid, but done twice. I have this part over on the right side and left side that I can do. So if we're rotating around the transverse axis, let me go ahead and mark that again. So this is this axis right here that we're talking about rotating around. It's the one that goes through the vertices. So if I rotate it around that, what do we end up with when we sketch this, or what's the sketch look like? I'm going to start with the one over here on the right side here, but pick whichever one you want to start with. So we'll end up with something about like this for the top of it. I'll draw another one of these down here. Again, the part out front should be solid, and the part behind should be a dotted line. Do the same thing over here on this other side. Give it the same perspective, though. So this time it's going to be dotted around behind. Draw another one of those here, right here. And you got yourself a nice little hyperboloid of two sheets. And again, we call it a hyperboloid of two sheets there because of the fact that you end up with two parts to this. Two distinct parts, two distinct surfaces. And the last one for us is the hyperboloid of one sheet. And it's called the hyperboloid of one sheet because you're going to end up with one skin here, if you will, when you rotate this around, as opposed to two that we saw in the previous one. We're rotating around the conjugate axis this time. So the conjugate axis is the axis that does not go through the hyperbola. Goes through the center, but not through the hyperbola. So we're rotating around this axis right here. And so when we rotate this around, we end up with something that looks like this. There's the top of it. And we'll draw a couple more of those. I've got another one of those right here. Again, dotted lines for what goes behind and solid lines for what's up front. There's another one here. It almost looks like a cooling tower at the nuclear plant, might be what that looks like there. Versus the hyperboloid of two sheets kind of has that appearance of being two paraboloids. They're not parabolas because there's asymptotes you're approaching, but it's kind of what it looks like. All right, so those are the 5 quadric surfaces that we can end up with, depending on what you start out with, whether you've got yourself a parabola, an ellipse, or a hyperbola. So let's take a look at an example here. Look at example 1 there on 516. So sketch the hyperboloid formed by rotating about the y-axis the hyperbola negative 9x squared plus y squared equals 9 from 0 to 2. All right, so we got ourselves a hyperbola. We should be able to tell that from the equation, but they told us that anyways. It was negative 9x squared plus y squared equals 9, and we're going from 0 to 2. All right. Now they give us a restriction on the domain here for us because the fact that the hyperbola goes on forever. Realize if we were doing this for an ellipse, I wouldn't need that restriction. If I was doing it for a parabola, I would need it. Okay, so some of these go on forever, and so I need a restriction on the domain for it. All right, let's first get this into its center radius form so that I can see where the center's at, and I can determine what the x dilation and y dilation are, and I can come up with a sketch of the hyperbola first. So to do that, we've got to divide by the 9, so we're going to end up with a negative x squared. And we'll end up with plus y squared divided by 9 equals 1. Remember that the center radius form has got this equal to 1, so that's why we want to divide by the 9. And in fact, I'm going to rewrite this so that I can see my h and my k and my d sub x and d sub y here in this. So I'll leave the negative out front. And actually, I'm going to go ahead and put in the hk. I was going to say I could leave that out, but I'm going to write it in there. So it's x minus 0. That's why I say I could leave that out. Divided by, and then there's nothing in the denominator, so that must be just a 1 then that I'm dividing by. So x minus 0 over 1 squared. And then we're going to add that to y minus 0 over 3 squared. And that's equal to 1. I like that form because that tells me right away where the center of this thing's at and what the x and my y dilation factors are. So I can use that now to come up with a pretty good sketch of this thing. So let's mark the center. The center is at 0, 0. Your x dilation, I guess one other thing we should note here is what direction this opens up in, right? The fact that the y is the positive term here, the x is the negative one, tells me it opens in the y direction. I guess I'm writing it here, but I could have actually written it from up above there. The original equation would tell me the same thing there, that the y is the positive one, so that tells me that it's open in the y direction. But anyway, we have it now. So since it opens up in the y direction, the dy tells me, my y dilation tells me how far it is from the center to the vertices. Let me mark those as well, so I'll put those in red here. So 3 units above the center will be right there, and 3 units below the center is right there. Those are my 2 vertices. And then I can sketch my asymptotes. Maybe I'll put this in green. My asymptotes there will have a slope of 3 over 1, a slope of 3. So you go over 1 unit from the center and up 3 is that point right there. Let's do that a couple of times here, just to get a few points that I can sketch this through. So over 3 and up 1, or sorry, over 1 and up 3. Do that same thing for going down here. Oops, I messed that up, I think. I did. Try that again. Start at the center. I should have drawn my center in a different color here, maybe. Maybe I'll put a green mark there so I don't mess that up again. Go over 1 and up 3. Over 1 and up 3. Over 1 and up 3. There we go. Now do the same thing going down here. So over 1 and down 3. Over 1, down 3. And so forth. So we've got a few points here that my asymptotes are going to go through. That will help me get a better sketch of this thing, I think. Maybe I should have used a different scale here for this. It's going to open up in the y direction and squeeze really tight here between these asymptotes. But anyways, there's our asymptotes. In fact, to give me even a better sketch here, since they gave us the domain that we're working in from 0 to 2, I know that at x equals 0 that I've got my vertices here marked. The question is, where am I going to be at x equals 2? So let's take and plug x equals 2 into the equation there and see what we have. It really doesn't matter which equation we use, so I'm going to pick that first equation they gave us. If I take, let me write that down, I'm going to plug in x equals 2. And again, I'm plugging in x equals 2 because that was the domain they gave us. They said to go from x equals 0 to x equals 2. I already know what's happening at 0. Question is, what's happening on the other end? So I've got a negative 9 times 2 squared plus y squared equals 9. Again, you can plug this into any one of the equations here. It won't matter which one you use. So 9 times, or negative 9 times 4 is a negative 36 plus y squared is equal to 9. So y squared is equal to 9 and 36 is 45. Okay, so y is equal to plus or minus the square root of 45. Square root of 49 is 7, so we're just slightly below 7 is what that tells me. If you want to get your calculator and get a more accurate number, you can. But I just want to have an idea of what point am I supposed to be approaching. So at x equals 2, so when I go over to 2, here's x equals 2, I should be up here at 7. I should get a few numbers on these. So this is at 2, this is at 3, this is at 6, this would be up here at 9, okay. So I'm supposed to be at x equals 2, square root of 45, I said, yeah, was about 7. So somewhere about right here, it looks like I'm supposed to be heading towards, somewhere in here. Okay, so I can sketch what this looks like. I'm going to sketch both sides of this here. So at x equals 2, we're just below 7 here. So it must look something about like this. And I can do the same thing down below. should mark those same values here. So this is at -3. Here is -6. Here's a -9. All right, so here is going to be 7. We're just below, actually just above, -7. -2, same story. Okay, so we end up with a sketch that does something like this. All right, there is our hyperbola on the domain they've specified. Now we want to rotate this around, which axis did it say? Rotate this around the y-axis. So we're going to rotate around this axis right here. All right, so let's sketch to see what we end up with here. When we rotate around this axis, we're going to end up with something that looks kind of like this. So it looks like we end up with a hyperboloid of 2 sheets is what we have here. Since we rotated around the, what is the transverse axis actually? They said rotate around the y-axis. Turns out that's the transverse axis. All right, that's all they want us to do, is sketch the hyperboloid form by rotating it around that axis there. There we go. That right there is the end of the first half of section 10.4.